For this lesson objective video, we are going to discuss thermal efficiency of a vapor power cycle. Before we discuss the thermal efficiency of a complete vapor power cycle, let's just review our generic thermal efficiency for any power cycle or any heat engine, as it were. So let's draw our high temperature reservoir, which has some temperature T sub H, and our low temperature reservoir that has some associated temperature T sub L. And in between there I have some cycle, generic cycle I'll draw with a little circle. And I'm going to surround that circle with this green dotted line. That's to indicate the boundary of my system. Because this is a heat engine or a power cycle, we are going to generate power through heat transfer from the high to low temperature reservoir. So I have heat transfer coming from the high temperature reservoir into my system, and I have heat transfer coming from my system as a loss to my low temperature reservoir. And the result is an output of work or net work out of my system. So thermal efficiency describes the performance for a power cycle. And so the thermal efficiency is my desired over my required, or what's sought versus what's bought. What do I want? What do I have to pay for it? And so for a heat engine or power cycle, I obviously want to produce power or net work out of the cycle. And that's going to cost me. My required is my rate of heat transfer, in this case my heat transfer, from the high temperature reservoir into my system. And I can write that as a ratio of the power over the rate of heat transfer, or the work per unit mass divided by the heat transfer per unit mass. It makes no difference. They all have the same ratio. So that's for any power cycle. Recalling the fact, because this is a cycle, my total energy change is equal to 0. If I neglect kinetic and potential energies, that means my heat transfer equals, my net heat transfer equals my net work. And so I can substitute the sum of the heat transfers into the numerator, my thermal efficiency as my desired, in case I don't have that information. And I can just simplify that to my thermal efficiency equals 1 plus the heat transfer from the low temperature reservoir divided by the heat transfer from the high temperature reservoir. And any heat transfer should be between 0 and 1, 1 being ideal, a perfect system, which doesn't exist. So I should be between 0 and 1 for my thermal efficiency. So how does this relate to our vapor power cycle? Well, where I have that generic circle for any cycle, I'm going to replace that with my entire vapor power cycle. So I look at the macro view, and now I look at my system boundaries, and I put that micro, that vapor power cycle into that system. And so now I'm looking at that system, and it's completely surrounded by that box. So let's change our nomenclature a little bit. I have heat transfer coming from the high temperature reservoir into my steam generator. That would be the rate of heat transfer from state 2 to state 3 to turn that water into steam. I would also have heat transfer out of my system into the low temperature reservoir coming out of the condenser in order to turn that steam back into water. And so that's my rate of heat transfer from state 4 to state 1. And I still have net work coming out of the system, but this is per unit time, so let's change that to net power coming out of the system. Now note that that's the net power coming out of the system, not just the turbine, and I'll talk about that more in a second. Let's look at our thermal efficiency desired versus required. So using the nomenclature we have now, it's just our rate of work, or our power, net power, divided by the rate of heat transfer from state 2 to state 3, or into our steam generator, into our system. Well, let's look at this this net power. Notice that I've written this as the sum of the power from state 1 to state 2 that's running the pump, that power required to run the pump, plus the power generated by the turbine. Remember, turbines produce power, pumps require power. In this case, I have it parasitic or slaved, so the pump is being run by some of the turbine power. Not all the turbine power, just some of it. And so the sum of those two powers would give me the net power out of my system. And remember, you're hip to win. Work in is negative, so work in the pump is negative. Work out of the turbine is positive. That's still divided by the rate of heat transfer from 2 to 3. Now later on we're going to get to more advanced vapor power cycles with regeneration, cogeneration, reheat, and our numbering sequence will be a little bit different. So let's not use the numbering sequence. Let's just call the rate of heat transfer from 2 to 3. Let's just call that our rate of heat transfer into our vapor power cycle. And then coming out of our cycle, we have that rate of heat transfer out. Let's just call that rate of heat transfer out instead of rate of heat transfer from 4 to 1, just to keep it generic. And so generically, for a vapor power cycle, our thermal efficiency is our net power divided by our rate of heat transfer into the system. Let's put a little yellow bubble around that. We'll keep that one. Now, how do the rest of the relationships work? Well, I had that sum of the heat transfer equals my net work. Well, let's just change that to rates, and let's change the subscripts to in and out. So that's the rate of heat transfer in plus the rate of heat transfer out equals our net power. And let's just do the same thing here in our thermal efficiency equation. We're just going to replace this with rates and our subscripts in and out. So we get our sum of our rate of heat transfers out divided by the rate of our heat transfer in, and I can simplify that algebraically to 1 plus the ratio of the heat transfer out to the rate of heat transfer in. And the thermal efficiency doesn't change. It's still between 0 and 1. So let's shade that yellow. We'll keep that. Now these aren't any different than the relationships you learned for in Chapter 5. We talked about generic cycles, but now we're just applying it specifically to vapor power cycles. And so you can see kind of the macro view. Now we're going into a little bit micro view. And these, since they have different subscripts, we have different equation numbers for these, but they're derived exactly the same. It's equation 8.13 and equation 8.14. See your instructor if you have any questions, and enjoy the video.